Hey everybody, just want to welcome you to Module 2, Lecture 1 for ME 171. In this lecture here, we're going to go through and finish up a little bit more with the Introduction to Design, and then go through a few example problems together. So now moving on to ecological considerations within the design process here, we can see is what we have here is a industrial life cycle right here for products. So we can see we have our raw materials that we use to produce the products. It goes into production. From there, it goes into distribution, use, reaches the end of its life and becomes waste. So these are all different things that we need to consider along the way when we're talking about the ecological impact of the rubber product we're designing. So we're talking about design here, design for durability and reliability, adaptable design for repairability, it's going to make it last longer and not become waste, remanufacturability and reusability. Can individual components within this be reused and not be put into a landfill? Obsolescence right here, recyclable and disposable with minimal impact. So which components, if they aren't able to be reused or remanufactured, can they be recycled? Is it made out of material that can be recycled? Is it biodegradable? Is it disposable with minimal impact? How is it going to affect the earth if it is sent to a landfill? What are the effects from there? So those are all things to consider, especially from the beginning as we're choosing the materials that we're designing it out of and the production process. Both of those right there, even in distribution. Talk about distribution, you got your packaging materials and stuff like that, and that stuff's going to be thrown away right away when the user gets the product. Those are immediately going to become waste. So can they be recycled? Are they biodegradable? Things like that are going to become important within this process. So as we talk about the ecological impacts here, we really want to think about this natural biological life cycle here, where the types of materials we choose are important, non-renewable resources versus renewable resources. So in any cases we can, we should really try to choose these renewable resources. So we come down here and we think about are they toxic, organic, inorganics? We really want to try to go with those organic materials that are non-toxic so that we can go back in. There'll be some natural decay. It goes right back to the earth. So we have this biological, natural life cycle occurring there just based upon the type of resources and materials we choose to use within our products. So this is something that is a concern and something within our design process that we really do want to consider is this ecological impact right from the beginning of our design process. It may be a little bit more cost. So these are things that are going to be factored in with the rest of our budget and the rest of our design criteria, but it's something that is important that we want to consider is the type of resources, toxics, inorganic materials, and this whole natural life cycle and how that is going to tie in with the other life cycle, our industrial life cycle, our product life cycle over here that we talked about. We take those materials, hopefully it is a renewable resource, non-toxic organic material that we can utilize, go into production, choose those production processes that don't produce any toxic outputs. They don't, anything that is waste from there is an organic material that has a natural decay and can go back in to the earth without an issue. The distribution, what we choose for packaging, can it be biodegradable packaging that we utilize there? Anything that is going to be used that isn't, necessarily biodegradable or a natural organic material, can it be reused? Let's design it so it can be remanufactured, rebuilt, repurposed from there. So all of these things are important. These two natural and product life cycles, or biological and industrial life cycles, tie in together with each other, and we need to think about how they work together. So that being said, our product life cycle does influence our environmental life cycle. So what's coming in? We need to ask ourselves what's coming into it. What are the materials? What's the energy requirements? So that's another thing that we haven't really considered too much here is how is it powered? Is it hydropowered? Is it solar powered? Is it wind powered? All those things are important as well with the ecological process here and how these two life cycles tie into each other. What's going out? What's being waste? What's being produced out? Is it a factory where there's going to be smoke stacks and coming out, or is it just going to be steam that's released? Things like that are something to consider. All of your waste materials, water, gases, things like that, and how does that affect the environment? What's going to be left behind afterwards? What are your scraps? What is your waste? What are the sources of these materials? What waste, what's left behind as far as the energy goes? All those type of things. Is it a diesel engine? Is it a gasoline engine? Or is it something that's clean burning? All those things are going to be important. Make sure you determine what's reusable, what's not reusable, what's recyclable, what's not recyclable components there, because the things that are not recyclable and are not reusable are going to be things that are left behind and end up in a landfill. Maybe try to choose those so that they're biodegradable, things like that, or try to minimize these number of things so that things can be reused and recycled. Who's affected? So you got to think of, not just the user, but also the manufacturer, the other people in society, all those things of who's actually going to be affected by this. So continuing on with ecological concerns here, there are some standards that we can follow. There's some various ASTM standards, there's some ISO standards that we can reference as well. This is something we really want to consider, this LCA or the life cycle assessment as well. So these are all things I would recommend looking into when we're doing your regulations, as far as even like OSHA and FDA and stuff like that. Take a look at some of these other standards related to the ecological effects of the design process as well. Now, relating back to Segway again, this is something that they did consider and how they pushed their product there, and they did some of this analysis. So, example here, if we're able to replace 10% of the 900 million 3-mile car trips within eco-friendly Segway, there would be this many fewer, 62 million fewer gallons of gas consumed and 286 million fewer pounds of CO2 emitted every day. So this is great. The ecological benefits of this are fantastic. And this is something to also consider, even though we're talking about design and engineering, a lot of times we need funding, we need backers, we need investors, and we need a business plan. So things like this are very important to understand how to write. What makes your product stand out, makes it better for whether it's a better performance, cheaper, more reliable, better ecological impacts like that. This is something that's important to be able to present these quick. Even if we only replace 10%, we're going to do millions less gallons and millions less pounds of CO2. Things like that are what they want to see. A lot of these pitches that you're going to make to investors to get grants, all this, are going to want these type of statistics. So this is, outside of it being the Segway thing, something to consider is quick, good statistics like this are very important. So I have a flow chart here talking about the design process here for a design project here. This is something to consider, especially with the design project for this course, to take a look at this even prior to really jumping into any of your ideas. We can see we broke this down into the conceptual design portion on the top and the embodiment design on the bottom here, where you define the problem. What problem are you addressing with the product that you're designing? What is your problem statement? From there, once you have that kind of down, you have the problem defined, you start gathering information. Go to the internet, take a look at existing patents. Does somebody already have a patent on this? What other existing products out there are on market already? All those type of things. You might want to reference some journal articles, trade journals, talk to consultants, things like that. All different great places to gather information related to the project and the product you're designing. Concept generation, brainstorming methods. You sit down with your group, whether it's in person, on Teams, whatever it is, come up with these different ideas, a whole list of different things, some systematic design methods, functional models. But these brainstorming sessions are very important, and you guys can all bounce ideas off each other in a positive manner for some of this concept generation. Now, once you have this big long list of them and you guys have all put this together and done this brainstorming session, you want to evaluate some of these concepts. Maybe eliminate some right away, do some decision making, take and do some comparison charts, benefits of one versus the other, all those type of things, put them into a decision matrix, go through and kind of narrow those down and evaluate the ones and come out with a better list. From there, you can get into some of the product architecture and arrangement of the physical elements. From that, we talk about now getting into our configuration design, which is going to be our preliminary selection of materials, what type of manufacturing process, and those two kind of play off each other. The type of materials you choose are going to dictate the manufacturing processes that are available for those types of materials. Talk about doing some modeling, getting into some SolidWorks models, some FEAs, talking about dimensioning, the size of the parts, which then incorporates along with size and material type. There's your weight and your cost start to come into play right there. Then you get into your parametric design, robust design, set your tolerances from there, and from that you can get into the detail design there, where you really dive into those engineering drawings, CAD models, FEA, and finalizing everything. Something to also think about within this whole design process is how the individual sections of this all interact with each other. It's not necessarily going to be a linear set of events that you're going to follow. Things are going to depend upon each other. So we discussed that briefly with a couple of the different topics already. So think about something right here. We talk about the form. You got all these different constraints, configurations, connections, all the different components. and different materials you're going to select for those. Well, the materials are going to affect over here the production. So the production methods, your manufacturing, your assembly, all those are going to be dependent upon the materials and also going to be dependent upon what components actually are. So these are all going to play off each other, and we had to make sure that they are all working interactively together and utilizing it. So let's just say we choose a stainless steel buckle. So what type of our manufacturing process are we allowed to use for something that needs that level of detail for the buckle there, and that small machining processes right there associated with the features of that in a stainless steel? So what things can we utilize for stainless steel for that there? Whereas instead of doing stainless steel, we decided to go with plastic. All of a sudden, we have different types of production. We could do some 3D printing, some mold, injection molding, things like that we couldn't necessarily do if we were dealing with stainless steel. But again, maybe it's a small, teeny little buckle, and there's a ton of individual parts within that there. So all of a sudden, yeah, we might be able to, do the molding for the lever arm of the buckle, but for the stainless steel base of the buckle, then we need to do some type of CNC machining, but then there's springs in there for the assembly process that are going to take manual assembly to do, and there's not an automated process for that. So we're kind of back and forth between what materials we're selecting, what the components are, what the configurations of those components are, and our production methods, and we want to make sure that everything functions correctly. So as we continue on with our design project here, something to think about is the customer needs. So this is something that we're going to get at the very beginning usually of any of these type of products. Somebody may come to us with what they want, what they need. We need to make sure that we understand very clearly all of their needs and have these written down in an organized manner so that we can determine if we have the capabilities, the knowledge, the skill set to even start this project for them. And if we do have that, we need to make sure that we understand exactly what they want, what their needs are, so that we can meet their needs along the way of this entire design project. So whatever their concepts are, their numbers, everything they have, we need to make sure we have all this information from the customer for what their needs are. So now we need to do the needs identification here. So how can we do this here? Well, there's different methods how we can gather this information from the customer, the client, whatever it may be. Meetings. So we have a lot of face-to-face meetings, virtual meetings, whatever it may be. Really ask the important questions to make sure we have a clear, concise understanding of what that customer, that client wants from us, what the regulations, specifications need to be for that product. Are there certain weight, cost, functionality, fit, clearances, any of those type of things that are become important. We need to have those all clearly stated. We don't want to find that out once we get down past prototyping and getting ready for production. Like, oh yeah, that's 2 inches too big. It's not going to work with the other thing. Well, we never specified that in the beginning with the customer needs. We never identified that need at the beginning. That's something we really need to do. So a lot of time needs to be spent in this initial stage of identifying the needs, whether it's your own project, your own product, or for a client. Now, for your own one, you got to ask yourself these tough questions. For the client, you really need to make sure you're asking the right questions to get into things that they may take for granted that they haven't communicated with you. Like, well, yeah, this is part of a bigger system. And you may not know that as the designer and the engineer. You might not know what they particularly do. So that's why it's important to do this market research, to do the reviews, to meet with them, to talk with them, and ask all of these important questions. From this, you can come up with a needs list within the needs identification. This is important, again, going back to documenting everything. You really want to clearly document everything all along the way, because it may be half a year later that you're coming back to certain portions of this project, and you want to go back and be able to reference it. So clearly documenting all this needs list is going to be very important. Things to do within this as well. What are needs versus wants? These are specifications that absolutely have to meet standards, fit, tolerances, whatever it is. These are wants. What is the importance value between what the wants are and what the needs are? What can be, compromised, modified, revised, and still make the customer happy, but meet all the absolutely positive requirement needs without sacrificing anything that's going to make the product not function correctly or not meet the needs that the customer wants. So this is something that's also important to do in this needs list here, is address all those. Put this into a matrix format, a spreadsheet with all the different, like, okay, this is top priority, absolutely needs to be made of stainless steel, but the weight is not quite as important, or the cost definitely needs to stay under $10,000 for this whole thing, but I'm willing to compromise on something else. So all of these, it's important to be able to reference back in a clear, concise manner of what these needs are and how they kind of fit into a grayscale area here for the importance value. So then we'll get into some specification development, talking about different methods associated with this. So things that we need to research a little bit more in this phase here, a little bit more of the prototyping, be it this physical model prototyping, CAD, 3D modeling, prototyping, taking a look at different patents. Are you able to get a patent of this? Does one already exist that you need to abide by and not jeopardize any of the limitations of that patent of the person who currently has it? Preliminary concept ideas, all those type of things need to be considered here when we're talking about a little bit more of the specification development here. Now, within these specifications, we need to make sure that these are going to be practical specifications. There's things that we can actually test. There are numerical values for things, competitive, what the requirements are for these, and everything is clear and concise within all these specifications. So again, this goes back again to, in my opinion, a lot of documentation, a lot of good, clear communication, very good researching, background information, all of your stuff as far as looking at existing patents, existing products on market, all the stuff becomes important, and making sure that we really do clearly and concisely document this the entire process. So now we'll get into another little flow chart here. I think these are great things to think about and ways to organize your thoughts within the design process here. So we'll take a look over here and what we have. We can see we start up here with our final specifications. We continue on from that final specifications. What do we do next? We'll review common approaches for the design specifications. Then we ask ourselves this question. Once we've done that review, is there any obvious design solution? If no, there's not an obvious design solution right there. There's a couple different things we consider that we need to weigh. We did generate design concepts for these unclear specifications so that we can answer yes, there is an obvious design solution. So from that there, once we do this here, either there is an obvious design solution or we just generate design concepts for whatever is unclear in the specifications, we can come back over here and say, okay, yes, we do have an obvious design solution. Then we get into research available alternatives. So within that, we ask ourselves, are there multiple viable concepts? And if the answer is no, there are not multiple viable concepts, then we come back up here and generate some more design concepts for that. Come back down to this section here until we get to the point that there are multiple viable concepts for this here. We answer yes. And then within these multiple viable concepts, we need to evaluate and rank. This kind of goes back to what we were talking about before, maybe make a little spreadsheet or a matrix here where we can actually evaluate and rank things and look at them clearly and say, okay, yes, this one is better because of this, this, and this. And there may be different areas for that evaluation. It might not just be one thing. It might be beneficial in one area and not beneficial in another. And it's great to have that all listed out so that we can compare and rank these. Now the question is, based upon, when we evaluate and rank these and we pick one there, is success likely with any of these? And if the answer is no, back up here to the beginning where we indicate the problem with the current specifications and change any specifications that we can from that there. If the answer is yes, that success is likely, then we need to select which one is going to be best of the design concepts and go on from there. So now I want to take a look at the kinematic equations and review these. We're going to be using for some of the applications and sample problems we'll be going through in lecture. So we have 5 variables and 5 different equations we're going to use for these. So this is where it's really important to take a look back at that initial setup page and understand, okay, this is what they've given me in the problem statement and this is what they're asking for. Because if we know what we have and what we're looking for, we can figure out which of these equations is going to line up with the information that we have. So we have VI, our initial velocity, VF, our final velocity, D being our distance, A being acceleration, and T being time. So if they give us in a problem that we have a distance and acceleration, we want to know how long it takes, well, we find an equation that involves these 3 variables but doesn't have velocities, or vice versa if they gave us an initial velocity and a time, and they want us to find a final velocity, things like that. Which problems can we use and which ones are going to have the variables that we need? So let's just take a look at this one here. Well, our final velocity is equal to our initial velocity plus acceleration and time, but doesn't involve distance at all. So if we don't have any distance term, this would be the equation that we would utilize. Now, if we do have a distance over here, but we don't have acceleration, we know that distance is equal to our initial velocity plus our final velocity divided by 2 times the time. Then we can come down here, what if we don't have time? Well, we have our final velocity squared is equal to our initial velocity squared plus 2 times our acceleration times the distance. Then we come down to this relationship over here. Well, this one has no final velocity, but we do have distance is equal to initial velocity times time plus 1/2 acceleration times time squared. And then finally we come over here where we have a final velocity but no initial velocity, and we have the distance is equal to our final velocity times time minus 1/2 at squared. So in summary, these are 5 different equations that we can utilize using 5 different variables here, depending on which variables they give us and which ones we don't know. So now let's go through an example problem here. We're going to take a look at problem RP 1.9 here. Now in this problem here, they're telling us that we have a car. They tell us the weight of the car is 300 pounds. We also know that this car is towing a single axis, 2-wheeled trailer, and we know the weight of the trailer is given to us as 1,500 pounds, and its initial velocity, it's moving at 60 miles per hour. So the other thing that they tell us here is that there are no brakes on the trailer, so the car by itself is going to be doing the full stopping power, and it can decelerate at 0.7 Gs. Again, this car produces the entire braking force because there's no brakes on the trailer. Now they want us to solve for several different things in this problem statement. So they want us to, 1, find the deceleration of the car and the attached trailer, so both of those together. They want us to determine the force applied to slow the car and the trailer. In this case here, this will be our frictional force here. And how far does the car and the trailer travel when slowing to a complete stop? So a complete stop is a little hint to tell us that it's going to reach a final velocity of 0. And they want us to also find out how long this is going to take. So in order to solve for all of these things that they want us to look for in this problem, we can use some of those kinematic equations based upon what they're asking us to solve for and what information we already have. So we can come down here and we could draw out a diagram to see what we have going on here. Well, within this diagram here, we have an initial velocity, which is 60 miles per hour. Do we want this to be in feet per second or miles per hour? This is something we'll have to decide. We have the weight of our trailer, and we have the weight of the car here, and we have some unknown frictional force that we're going to be solving for right here. And we also see we can have the normal forces acting back up from the weight of the car and the weight of the trailer. So the next thing that we want to do is create our setup page. We can take all the information that we've read through in the problem statement and given diagram there and write it down in a clear, organized manner that's easy to follow through. So what I want to do is write down everything that I'm given within that problem statement initial diagram here and 4 different things for each of these. I want the variable name, I want the numeric value, I want the unit that we're going to be using, and I want a statement relating back to how it relates to our problem. So this is W sub C, which is the weight of the car. It has a value of 3,000 in units of pounds right there. So now I can do the same thing with all the other given information. I have my V sub I, or my initial velocity of the car and the trailer, and this is 60 in units of miles per hour. I have my coefficient of friction, which is my mu of 0.7. There are no units of this, it's just 0.7. And then I have the weight of the trailer, which is W sub T for my variable name. This is equal to 1,500 pounds. Now from here I can come over and draw out a simplified version of my diagram. Now you can notice here I don't have any numeric values associated with this. I simply have the variable names, and that's to keep this diagram decluttered, neat, and organized, and easy to follow. If I were to put in values for everything, you can see it quickly becomes really disorganized and cluttered. So I can see here I have my trailer and I have my car. Now on my trailer I have my weight force of my trailer acting down and my normal force acting back up. I have for the car my normal force acting up, my weight force acting down. I can see my initial velocity here is moving over to the right, and I can see my frictional force is opposing my direction of motion and moving to the left. Now how does this relate to our chosen coordinate system? I've also put up my coordinate system I'm choosing here, which I'm saying positive x is moving to the right and positive y is going up. Now this becomes so important with sign convention, so we look down here and see, well, my weight forces would be negative according to my chosen coordinate system. My normal force would be positive. My initial velocity would be positive x direction, and my frictional force would be in the negative x direction here. So now I come down and see what did they ask me to solve for in this problem. Well, they asked me to solve for 4 different things. The first thing they asked me to solve for in part A here was my frictional force, which I'm calling F sub F. They also asked me to solve for my acceleration, A. Third, they asked me to solve for the time required to stop, my T. And in the last part here, D, they asked me to solve for the distance traveled until it stops, which would be my delta x. Now also on the setup page, you want to write down any assumptions that we're making. Well, the first assumption I'm making here is that the car and the trailer are stable during deceleration. The second thing is that the deceleration of the car and the trailer does not change the 3,000-pound car tire force on the pavement. So we can see that right up there is our normal force right here, would be that 3,000-pound car tire force that we're referring to. So once we've had the opportunity to read through the problem statement, take a look at the initial diagram, then create that setup page with all of our given information clearly labeled, exactly what we're supposed to be solving for labeled, all of our assumptions there, our next step is to begin our solution. So as we begin our solution here, the first thing that I like to do is figure out what are my key equations. And it's a lot easier to figure out what our key equations are if we have all of that given information clearly written down and labeled, and all of the things that we're looking to solve for in our find section clearly written down as well. So my key equations here, well, the first thing I'd ask to solve for is friction force. So our friction force, I have my governing equation here that my frictional force is equal to my coefficient of friction times my normal force right here. So there's my governing equation for my friction force. Another key equation I'm going to end up using here is F equals ma from Newton's second law. And then we have a couple of these different kinematic equations for the other things we're looking to solve for here. Delta x being one, velocity being the other. If we're looking for delta x, this is equal to the final velocity times time minus 1/2 my acceleration times time squared. And we have my final velocity here is equal to my initial velocity plus acceleration times time. So these are my 4 key equations for the 4 different things that I'll be solving for within this problem. So as we're solving these problems, the important thing to do is break them down into individual steps along the way. So there's 4 different parts to this problem. Let's look at each of these separately. The first part, part A right here, they asked us to solve for the frictional force here. So we go back to our governing equation that we just found here. Our frictional force governing equation is that F sub F is equal to mu, our coefficient of friction, times N, our normal force. Now you can see I've redrawn out here my initial schematic diagram that I created in my setup page here, just so I can reference back to it. You don't necessarily need to redraw this out in your homework solutions. You can flip back to that first page. For this presentation's sake, I've redrawn it over here. So what are they asking me to solve for in part A? They want us to solve for the frictional force. Here's my governing equation. My frictional force is equal to my coefficient of friction times my normal force of the car, where I can now take from my first page here, look back to my setup page and say, well, my coefficient of friction is given to me as 0.7. And my normal force of the car is equal to the weight force of the car, which is equal to 3,000 pounds. Now I can take these numeric values and plug them back into my governing equation here. Say that my frictional force is equal to my mu, which is 0.7, and my normal force of the car, which is 3,000 pounds. I can do my math, 0.7 times 3,000 pounds. I can see that the frictional force here I've solved for in part A is 2,100 in units of pounds. So that's another thing that we really do want to pay attention to is our units. In this case here, everything was in pounds. Friction does not have any units associated with it, so our final force is going to be the same as our weight force here, our normal force, which is 2,100 in units of pounds. So now what we want to do is move on to part B in our solution here. So part B, that asks us to solve for our deceleration. So we'll be looking for acceleration equations here in governing equations. So we're looking for the deceleration of the car and the trailer in part B. So we can go to Newton's second law as our governing equation. This involves force is equal to mass times acceleration. So there's the acceleration part that we're going to be looking for there, where we want to pay attention to what is mass. So we'll do a little side note over here and say that mass is equal to weight divided by our acceleration due to gravity. We know the acceleration due to gravity in the correct units that we're dealing with here, feet and second squared. So weight divided by 32.2 feet per second squared will give us our mass right there. So now we can go back to our governing equation. What we want to do is rearrange this and solve Newton's second law for acceleration. So we rearrange that there. We can divide both sides by mass. We end up with acceleration is equal to force divided by our mass. Now, a thing to think about here when we're talking about our weight, it's the weight total. This is the car and the trailer together when we're decelerating. So the total weight is going to be the weight of the car plus the weight of the trailer. So that's just something to think about as we start plugging into our governing equation here. So we take our governing equation, we say, okay, acceleration is equal to force divided by our mass. Well, our mass is equal to weight divided by acceleration to gravity, and weight is equal to our total weight. So our mass is equal to our total weight, the weight of the car, plus the weight of the trailer, divided by acceleration due to gravity. And this bottom term now is our mass from our governing equation from the rearrangement of Newton's second law. Our frictional force on the top here, our force on the top here is our frictional force, our F sub F there. We've already solved for that in part A of the problem statement there. So now we have our frictional force, 2,100 pounds, divided by the sum of the weight force of the car and the weight of the trailer, divided by our acceleration due to gravity. So that's 3,000 pounds plus 1,500 pounds, all divided by 32.2 feet per second squared. Pay attention to our units and do out unit analysis to make sure we get the units of our acceleration and what we should expect. So we simplify this down and we can say, okay, 3,000 plus 1,500 is 4,500 pounds divided by 32.2 feet per second squared. On the bottom, we still have our 2,100 in units of pounds up here on the top on our numerator there. So we can do that out. We can see the pounds on the top cancel with the pounds on the bottom. We're going to be left with just feet per second squared. So we can rearrange and put a 32.2 up here on the top like that. And we can see now when we do this out, we can plug and chug, plug this into a calculator, Excel, MATLAB, whatever you want, do this by hand. We find out we have acceleration is equal to 15 feet per second squared. And this is our acceleration. Our units do check out. This does make sense, feet per second squared for an acceleration. So this is our answer to part B. Now from there, we move on to part C. So in part C, they ask us to calculate the time it takes for the car to come to a stop. Well, if the car comes to a stop, what that's telling us is that our final velocity is equal to 0. So v sub f is equal to 0 there. We now have our acceleration we've just solved for on the previous section from part B here. Our acceleration is 15.03 feet per second squared. And our initial velocity is equal to 60 miles per hour, which we're paying attention now, everything else in feet per second. So we need to convert this miles per hour to feet per second. So our initial velocity when we do that conversion is 88 feet per second there. So with that information, now we can choose the correct governing equation. Well, we want the time it takes to stop. We have an initial velocity and a final velocity, and we have an acceleration there. So we can use this kinematic relationship here. Our final velocity is equal to our initial velocity plus our acceleration times time. So our final velocity is 0 because it comes to rest. Our initial velocity in the correct units is 88 feet per second. And we have our acceleration we solved for in part B of the problem here, which is 15.03, but this is negative. This is negative because it's moving, the deceleration acts in the negative x direction right here, and positive x is going to the right, so this opposes the direction. So this right here in deceleration is negative 15.07 feet per second. And we have time is our unknown value right here, so that's what we're solving. So we can rearrange this equation here, solve for time. We do that and we can say that negative 88 feet per second is equal to negative 15.03 in feet per second squared. Solve for time, rearrange, divide, and we end up with time is equal to negative 88 feet per second over negative 15.03 feet per second squared. Everything cancels except for our seconds on the bottom, which is great because when it's the inverse of that, it'll be back on the top when we solve for time. Time is equal to 5.855 seconds. The units check out. So now we have an answer for the time it takes for the car and trailer to stop for part C. Now from here, we move on to part D of the problem here. Part D asks us how far does the car and trailer travel before it comes to a stop. So we have our kinematic equation here. We can see delta x is how far, that's what we want to find. We have our VF when it comes to a stop, that's going to be 0. We now have a value for time, so we can plug in there. We have a value for acceleration, which we found as well, which is our deceleration. And we again have a value for time there. So we plug in, I like to make a little side note here. These are all the values I have that I can plug in here. My VF is 0 because it comes to a stop. My time is 5.855 seconds. So those are my units there. And my acceleration is a deceleration, so it's negative of 15.03 feet per second squared there. Go back to my governing equation here, plug in, V sub F is 0. My deceleration term right here is 15.03 negative, and my time over here is 5.855 right there. So I can take a look at everything right here. This is a squared term there, so it's second squared there, cancels with second squared there. So therefore the only units I have left are feet. So when I plug in here, my delta x is 252.62 in units of feet. That does check out as well. So now I've solved for the last thing that it asks to solve for in the fourth part, or part D of the problem right here, which is that how far does the car travel before it stops. So my delta x is given right here. Let's take a look at example problem 1.11. In this problem here, we have a block that weighs 3,000 pounds sliding down a flat surface, and an initial velocity given to us is 88 feet per second. Now the coefficient of friction between the block and that flat surface is given to us as 0.7. Now they want us to find the frictional force causing the block to slow, how far the block will travel in slowing to a stop, so we know it comes at final velocity of 0, and how many seconds does this take in order for it to reach that stop. They also ask us to do a couple more things. One, how much work was done to stop the block, and lastly, what was the initial kinetic energy of the block. So as we're reading through the problem statement, and we look down here at our initial diagram here, where we have our initial velocity, we have the block weight, we have our normal force, we have what our frictional force will be over here. And what we need to do is from this, take a look and say, okay, what was given and what are they asking us to solve for? Well, what was given was the weight. The weight was equal to 3,000 pounds. The initial velocity was given as 88 feet per second, and our coefficient of friction was given as mu is equal to 0.7. What do they ask us to solve for? Well, our frictional force, we're going to use the variable F for that. The distance traveled until it stops, we're going to use the variable S. And the time until it stops, we're going to use the variable T. They also ask us to solve for the work done to stop the block, which we're going to call W, and our initial kinetic energy of the block, which is our K sub E. So we take all this information from our initial diagram, initial problem statement, to create our setup page next. So now what we're going to do is create that setup page. So as I've mentioned, this is very important to have for any of the problems we're doing, whether it's a homework problem, example problem, or exam problem. We want to be able to reference back to this. So we need a way to clearly label what's given to us, what they're asking us to solve for, and any given initial diagram simplified down, along with our chosen coordinate system. So that's exactly what we do here. So the given information, again, 4 pieces of information within each of these: the variable, the numerical value, the unit, and how it relates to our problem. So we have W sub B, which is the weight of our block, which is 3,000 in units of pounds. And we can see here, I've written down this is the weight of the block. Then I have my initial velocity of the block, or V sub I, is equal to 88 feet per second. And the coefficient of friction, or mu, is equal to 0.7, which is unitless. Then I have my diagram over here on the right. You can see there's my surface, there's my block, there's my weight force right there. There's the frictional force that I'm going to be solving for between the block and the surface right there. My initial velocity moving over what I'm considering to be the positive x direction to the right. And I've called my positive y direction going up right there. Now, there's 5 different things now in this problem that they need us to solve for. In part A, we're going to solve for F sub F, or my frictional force required to slow the block. I'm going to solve in part B for S, which is the distance the block travels until it stops. C, I'm looking for T, which is the time it takes for the block to stop. In part D, I'm looking for W, or the work done to stop the block. And in part E, I'm looking for my KE, or my initial kinetic energy of the block. Now you can see in this section here, I've very clearly, in a nice organized manner, labeled everything. So I can come back and say, okay, in part A in my solution, I'm looking for the variable that I'm calling F sub F. What is this? This is my frictional force. Do the same thing down here. In part B, I'm looking for S. The variable name S, which is the distance the block travels until it stops. So I've taken everything from that problem statement initial diagram and really neatly organized it so I can reference back to the setup page as I'm going through. Now a problem like this becomes very important because there's 5 different things I'm solving for. And I want to make sure I solve for everything the problem asks me to solve for. So that's why I label these parts A through E so I can individually solve these one at a time. So the next thing we want to do is create our free body diagram right here. So we take our simplified version of our initial given diagram here with all the forces acting on it. So we can see we have the block, we have our weight force acting down here on the block, we have our frictional force over here, and we have our chosen coordinate system, positive y up, positive x to the right. And now what we want to do is take a look at just the block here and draw our free body diagram. And so that's what we do. We take our block, put it right down here. Here's our block right there. And we say, okay, in our block, what do we have going on here? Well, we have a couple different forces acting on it here. We have our frictional force right here, which is going in our negative x direction. There's our frictional force moving in our negative x direction. In our y direction, we have a positive normal force from the surface pushing up on the block, and our weight force of the block pushing down right here. So those are our 2 forces right there. So we can see if we were to do a summation of forces in our y direction, our only forces acting in our y direction are our normal force and our weight force. So therefore, our normal force is equal to our weight force. So next thing I want to do is take a look at my setup page, my free body diagram, all my given information, what they're asking me to solve for, and determine what are my key equations in this problem here. So my key equations right here, well, the first thing is going to be my frictional force that I need to solve for in part A. So I have my governing equation here. Frictional force is equal to my coefficient of friction times my normal force. So I can label everything here. N is my normal force. Mu is my coefficient of friction. F sub F is my frictional force. So I can have my general equation here, but quickly reference and know what I'm plugging in. Now, in Newton's second law will be my other governing equation here. This comes from equation 1.1 on page 14 of the textbook, and this says that F is equal to ma, where F is your force, m is your mass, and a is your acceleration. Now, acceleration, we can equate this to velocity per time. So acceleration is velocity divided by our time right here. So moving forward, some more of our governing equations we're going to utilize for this problem right here. We have our kinematic equations here, where v is equal to v sub I plus at. So my final velocity is equal to my initial velocity plus my acceleration times time. My change in distance is equal to my initial velocity times time plus 1/2 my acceleration times time squared. Again, pay attention to your units, pay attention to what your coordinate system you chose. Is that going to be positive or is that going to be negative based upon all that information? The other thing I'm going to be looking for here is work. So my general equation for work is work is equal to my frictional force times that distance s. And my kinetic energy general equation here is 1/2 mv squared, 1/2 mass times my velocity squared is equal to my kinetic energy. So now I can begin my solution. I have my setup page. I know what they've given me for information. I know what they're asking me to solve for. I've established my governing equations that I'm going to use. So now piece by piece, let's solve this. So let's start with just part A in our solution here. So in part A in our solution here, we have, they ask us to solve for the frictional force. So our frictional force, F sub F, is equal to mu times N, where mu is given to us as 0.7. Our N is our normal force, which we can find from our free body diagram, which is equal to our weight force, which is equal to 3,000 pounds. And our frictional force, F sub F here, when we plug in for our mu of 0.7 and our N of 3,000 pounds, our frictional force we find to be 2,100 pounds. So that is part A. We go back over to ask to solve for frictional force. Okay, we've done that. Part A is solved. So now moving on to part B, we're asked to solve for the distance that the block travels before it stops. So what we want to do is choose our governing equation right here. We're going to use our kinematic equations right there. You can see in general form what we have here is v naught, our initial velocity times time, plus 1/2 a, our acceleration times time squared, is equal to our delta x. Well, in our case here, we have a different variable name. We're going to call it delta s, and we're going to deal with our final velocity here, and we're going to have a negative acceleration here. So this is our rearrangement of that kinematic relationship there. Delta s is equal to vf, our final velocity, times time, minus 1/2 at squared. So what do we need? Well, we're going to need to know our final velocity. Our final velocity from the problem statement tells us it stops, so the final velocity is 0. Our time, t, time it takes for the block to stop. Our acceleration a, which is the acceleration of the block in our x direction there, so pay attention to sign convention according to our chosen coordinate system. So now the big question is, how do we solve this relationship here for our acceleration a? So in order to solve for acceleration, we can use Newton's second law. So recall that F is equal to ma, where m, in this case here, is our mass, which our mass we can write as our weight divided by acceleration due to gravity, or acceleration due to gravity for our problem here for dealing with feet and seconds is 32.2 feet per second squared. So we can plug in our value for our weight of 3,000 pounds divided by 32.2 in order to get our mass value there. So from Newton's second law, we want to find acceleration. So acceleration, we can rearrange Newton's second law and say that acceleration is equal to force divided by that mass. So acceleration is equal to our F sub F when we replace for our F here. This is our frictional force divided by m. So we can take this up here from our m and plug this in down here for our mass. So frictional force we've already solved for in part A is 2,100 pounds. Now our mass here is 3,000 divided by 32.2 from our weight divided by acceleration due to gravity there. So we can plug that in there and we can solve now for our acceleration. Acceleration is 22.54 in units when we do our unit analysis out of feet per second squared, which does make sense. Now this can be positive or negative, and this is going to depend upon is it accelerating or decelerating. So next, we can come over to part C. In part C, they ask us to solve for time, the time it takes for this to stop. So we go back to our general kinematic equations here. So we can use this relationship that we see here where we have that v sub f, our final velocity, is equal to our v sub I initial velocity plus our acceleration times time right here, where our final velocity is 0 because it comes to a stop there, so that simplifies down. Now I write down all my knowns. I can go back to my setup page, and I can go back through all parts A and B, and my solutions I found there, and I find that given from our setup page, our initial velocity is 88 feet per second, so I can plug that in for my v sub I there. My final velocity is 0 because it comes to a rest. I can plug that in there. My acceleration that I just solved for on the previous part of this problem here was 22.5 feet per second, and my time is unknown, which is exactly what I'm looking to solve for. So I can plug in everything there, one equation, one unknown. So 0 is equal to my initial velocity, 88 feet per second, plus my acceleration, which is 22.54, and times time, which is time what I'm looking for, so I can rearrange this and solve for time. So that's exactly what I do there. I plug in now v sub f, final velocity 0, 88 feet per second in positive direction. Positive x direction is my initial velocity moving positive to the right, plus my acceleration times time. Well, it's a deceleration. It's slowing it down, so make sure we put our sign convention in here as a negative 22.5 feet per second squared, times time over here. Now I come down here and I can say, okay, let's rearrange this and solve for time. So I can move a few things around. I end up with negative 88 feet per second is equal to negative 22.54 feet per second squared times time. Divide both sides by this negative 22.54. Find that time is equal to negative 88 feet per second divided by 22.54 feet per second squared. My feet per second cancels with my feet per second here. I'm left with just a second on the bottom right here, which would make a second on the top when I invert that. So time is equal to 3.904 in units of seconds. The units check out. So this is my answer to part C for the time requirement. Now we can plug in this T and the A back into part B. So if we go back into our general equation in part B right here, and I have my A is equal to 22.54 feet per second squared, and I have my time is equal to 3.904 seconds right there. I can plug back in over here. Well, this right here, first term of this kinematic equation goes to 0 because it stops. So this becomes 0. So 0 times t is 0. Minus 1/2 at squared. So minus 1/2 negative acceleration because it's a deceleration. Negative 22.54 times my time squared right here. So my time is 3.904 quantity squared right there. So I can see as I move forward through this here, my negative and my negative cancel out and both become positives right there. Do my math out right here, and I end up with a delta S, or my distance here, of positive 171.78 units of feet when I do out my unit analysis, which does check. So therefore, delta S is equal to 171.78 feet. So the next thing we do is we move on to part D. In part D, they ask us to solve for the work. Now work is force times the applied distance here. So we can say there's our general governing equation right there. Work is equal to F times S, or S, it could be our delta X depending on how we've labeled it here, where F is equal to our frictional force, which we've already solved for, 2,100 pounds, and S is equal to 171.78 feet, which we just solved for in previous part C. Plug in our known values. So our known values right here, work is equal to my frictional force right there, plug that in there is 2,100 pounds, and my distance is 171.78 feet. So this is feet times pounds, or foot-pounds for my units. That's correct for work. Plug this in, we end up with 360,738 foot-pounds for our work. So from here, we can move on to our final part that we're solving for, part E, which had asked us to solve for our kinetic energy. Now we recall our general equation for kinetic energy is 1/2 mv squared, where m is our weight divided by 32.2, acceleration due to gravity, and our velocity here was given to us as 88 feet per second right there. So we can plug in our known values into our general equation for kinetic energy. This is equal to 1/2 our mass, or our weight divided by acceleration due to gravity in units of lbm right there, pound mass, and our velocity in units of feet per second of 88 with our value there. Plug that out. Run this through to our unit analysis. Kinetic energy is 360,738 foot-pounds for our kinetic energy as well.